Welcome back. My first engine build will be this Wig-Wag engine from 8 Swash. 8 has got a website where you can download plans for his engines. Now, this is the the simplest engine he's got on his website, so I think for me it will be a good start. Now he's got a variety of engines, very complicated. Some of them, like this one, will be very easy. So I'm going to leave you with links to his YouTube page and his website, so that if you're interested in building one of his engines or check him out, then you can do so. And I would suggest you support the guy. Now he gives this plans away for free. You can download it at no cost. And yeah, they're very easy to follow and well laid out. Everything that you need is in here, even the reference to what materials you're supposed to use. I've cast this piece of stock here. It's a little bit undersized for a flywheel, but I'm gonna make a little bit of modifications. Instead of, after I've cleaned up, I'll see what the OD of the stock will be, and then adjust the width to keep the same weight. I might increase it a little bit just to keep the angular momentum on par. So I hope you can enjoy this build. Something new for me and something different for the channel. Okay, my first operation is to clean up this face here and to clean up the OD so that I can determine how thick I must make it or cut it for my flywheel. The leftovers will be used for a crank disc. Now the plans are designed such that you can use off-the-shelf stock that you can buy, but I've opted to cast the major pieces, especially the bronze and brass stock or aluminium stock that you're supposed to use, because it's easier for me to cast it and comes at no cost except for the gas that I'm using. So yeah, this is aluminium bronze. It's 10% aluminium, so it's going to be hard. So I want to keep it hard and or use hard stock so that it doesn't scratch up after I'm finished, because this will be a showcase piece, and it will definitely be functional. But I mean, it's my first engine, so it needs to go to be put up as a trophy. So yeah, let's start up. Okay, after about 15 passes, this whole just kept keep on getting bigger, and currently is around 6.5 millimeters deep. So what I'm going to do is I'm going to put it in a bandsaw and then chop it off. That little section there, it will save me a bit of machining time. This void is running quite deep. I've cut around about 5 millimeters off the face here, and as you can see, it's quite a significant void. So there's still remnants of it, so I need to cut it out. I'll do that off camera. Okay, have to rethink my strategy here. Now, the cleanup cut here is about 13 millimeters deep to a nominal size of 65 millimeters. But my problem is if I turn it around and I cut the other side, I'll be left with a little niblet here in the middle, which I can't clean up. And the stock is still too big for my internal jaws. So what I'm going to do is I'm going to turn down this diameter down to 40 millimeters, which is the size of the crank web. But I'm going to make it 10 millimeters deep because the crank web needs, crank plate needs to be 8 millimeters thick. So I'm going to cut it 10 millimeters so that I have clearance for my bandsaw blade and enough to clean it up afterwards. And then if I take it down to 40 millimeters, it should fit into my internal jaws when I flip it around, and then I can do the OD from there. So in order to not waste any material here, I think that's a strategy I'm going to use. Next up, I'm going to cut a groove here in the face. I've got my threading tool centered here on the face, and then I'm going to zero my arrow and use that as a reference to mark out the positions to which I'm supposed to cut the recess in the face here. I need to leave the web in the middle at 15 millimeters, and then on the outside I need to leave the lip here of 7.5 millimeters. And I need to cut it 55 millimeters deep. Cutting out this recess was quite a mission for me because of tool vibration. I've reduced the speed, helped a little bit, but the boring bar, in order for me to show you what I'm doing here, caused a lot of vibration because of the long stick out. But it cleaned up nicely. The depth is 0.3 millimeters deeper than it's supposed to be, and this border here or lip is overshot by 0.05 millimeters. But yeah, it's for myself, so I'm not going to worry too much about it. Now I need to drill in a 6 millimeter hole. It's going to go right through because the crank disc is also going to be 6 millimeter, the bore. Now I don't have a 6 millimeter reamer. I don't have any reamers for that matter. So what I'm going to do is I'm going to drill a 5.5 millimeter hole through, and then push in what's his name, a 6 millimeter end mill, but I'm going to lock my coil of my tailstock as tight as I can without locking it fully so that it doesn't advance into the part, just to prevent any lateral movement on the tailstock, so to get the hole as precise as possible with what I've got here. Unfortunately, the hole did run out to the side, so I flipped it around and drilled it with an end mill from the other side. Then I've taken it up to 8 millimeters. So I'll just adjust the shaft to match. At least it's running through now. Okay, I'm not going to split the two halves now, or the two parts. What I'm going to do is I'm going to use the flywheel to hold it down into a 4-jaw chuck on my rotary table, and I'm going to mill out the features of the crank disc, and then once that is done, then I'll split it. Okay, I'm going to do these cutouts on a rotary table and also this recess in here. Now this whole engine can be built on a milling machine. You don't need to have a lathe to do this build. So if you don't have a lathe but you do have a milling machine, you can still do it using a rotary table. Everything can be made on here. Now that's the operations that I've done on the lathe. This recess that I've cut out on the flywheel. The back side of the flywheel, I'm gonna cut that very same recess out using the milling machine, just to demonstrate. This cutouts here strictly don't need to do it on a rotary table. It's just a 90-degree cutout that I need to do. And there's a radius here of 12 millimeters. I'm going to start off with 8 millimeter with offset of 4 millimeters just to do the bulk. And then bring in my bigger 12 millimeter end mill to finish out that corner. Now I've centered it on the vise here, not the vise, the chuck. And I've centered it on my spindle. Just gonna zero everything on the DRO. Now what I'm gonna do is I'm gonna use my STM function on the DRO on a couple of positions on the STM function to zero everything, and then work out my offsets, move the table over to those offsets, then zero it again so that I have multiple references for these radii and the positions of the holes and my absolute the position that I'm starting off from. That's just my way of doing it a lot easier for myself, of making it easier for myself. And as you can see, this is the reason why I've just opted to not separate the parts, but keep them together until I finish up the milling operations of the crank disc. Okay, what I've done here is I've offset my end mill 6 millimeters towards the chuck of my mill. That will give me a 12 millimeter clearance so that when I cut with my 12 millimeter end mill, when I do the finishing cuts, that I will land up right in line with the center of this hole here. And I've also moved it towards the left by 13.5 millimeters so that I can use have my 7.5 millimeters offset from the center, because this width here should be 15 millimeters. So 6 plus 7.5 give you 13.5. So you'll end up somewhere here. So what I'm going to do is I'm going to mill out this section here with an 8 millimeter end mill, just rough it out. After I've zeroed my DRO and STM1, then change the tool and then do the rest of the cutout. Now I'm not worried about marring up the surface here at the bottom because I've left myself a little bit of meat here to clean up afterwards. Okay, the hole for a crank pin is 15 millimeters from the center, and dead center in this little web here. Okay, you guys have no idea how much of tool pressure it takes to get the stuff drilled and milled. Now, I've tried with my high-speed steel to cut these edges here, and it just didn't want to cut. Now, I was lucky enough to be able to plunge cut these radii here on the sides. I've worked from a 10 millimeter up to a 12 until it got my radius here. Advanced the table as I was doing it, and I managed to cut it. Now side milling, I, I can forget about it. My high speed steel just doesn't want to cut it. So I had to revert back to my 8 millimeter carbide, and it managed to cut it very beautifully. So I tried to blend it into the corners as nice as I could, but at least it was a success. I managed to land my 15 millimeter width here. So what I'm gonna do now, there's a little recess that needs to go in here. It's more aesthetics than functional, and this portion here needs to be 1 millimeter deeper than the rest of the crank disc, because there's a bushing or something that needs to go in here according to the sketch. So I'm gonna mill this piece out and then make a nice radius inside. I've got this little chip here on the side. Looks like the metal didn't melt there properly. So what I'm gonna do is I'm gonna chamfer the inside edge. Here's the alternative method you can use to make your flywheel if you've got only a mill and not a lathe. I'm going to use the rotary table to take off the top and to cut in the recess. Okay, now I'm going to do the recess on this side. One more up to go. Okay, we're all done. Now I was only planning on doing the flywheel, but because of the work holding solution that I thought of afterwards, decided to do the crank disc as well. There's a little bit of inclusions there, but I think it's fine or good enough. Now this side I've done with a lathe, and this side I've done with the mill, and the finish is pretty comparable. And goes to show that you can use any machine to do the same job. Lathe is just a little bit faster, but you can obtain quite a good surface finish with a mill with a bit of patience. And strange enough, this recess didn't take as long to cut as with the end mill than it did with the lathe, because I didn't have to do a lot of tool changes. Yeah, I hope you enjoyed this build. There's a lot more to come. Cheers.